Hello, my name is Carolina Cantu Oliva, and today I will be performing a spectrophotometry simulation. The purpose of this experiment is to use spectrophotometry and Beer's law to determine the concentration of an unknown solution. We then create a calibration curve from known concentrations and finding the unknown sample's concentration based on its absorbance. To summarize my experiment, spectrophotometry was used to study how light interacts with colored solutions and how this relationship can be used to find unknown concentrations. The stock blue number 1 dye was chosen because its color absorbs light at a measurable wavelength. By preparing solutions with known concentrations, it became clear that adding more dye caused less light to pass through and increased the absorbance. Using these pairs of concentration and absorbance values, a calibration curve was created to show Beer's law. The linear graph showed that absorbance increases directly with concentration, meaning the dye behaves in a predictable way when absorbing light. After establishing this pattern with the known solutions, the same measurement method was applied to an unknown sample. Because the unknown's absorbance fell along the same line, its concentration could be calculated using the slope from the calibration curve. This experiment demonstrates that spectrophotometry is a dependable method for determining the concentration of substances in solution and shows how light absorption relates to chemical analysis. Today we are performing the spectrophotometry simulation to determine the concentration of an unknown solution. The purpose of this experiment is to use Beer's law to relate absorbance to concentration and use a calibration curve to find the unknown. So first I will prepare a series of test tubes to find the concentrations by diluting the stock blue number 1 dye solution with distilled water. Okay. After I prepare all the test tubes, I place each solution into the spectrophotometer. The spectrophotometer measures the amount of light a substance absorbs, making sure to zero the instrument using the blank first. For each of the solutions, I recorded the percentage transmittance as 630 nm. And then now I will be using our unknown substance, and this is how we're going to see the amount of light this absorbs. Okay, my measured values range from 49% for the highly concentrated stock solution to 87% for the most diluted sample. Even though this does show the results in our data, if we wanted to do this manually, I would convert the measured into decimals by dividing by 100 and then calculate the absorbance. My absorbance values range from about 0.0605 for the most dilute, and I plot the absorbance versus concentration to create a calibration curve. The graph shows a linear graph, which confirms Beer's law that the absorbance is proportional to the path length b through the sample and concentration of the absorbing species. The slope of my line is 0.1358 absorption per concentration. Next, I measure the percent transmittance of the unknown drink solution. It is measured 39%, which converts to a absorbance of 0.4089. To find the concentration, I apply the absorbance of the unknown to the calibration line equation using the relationship concentration equals absorbance divided by slope, which equals 0.4089 divided by 0.1358. I calculate the unknown concentration to be 3.011. This experiment shows how spectrophotometry can be used to qualify the concentration of a solution by relating absorbance to concentration through a calibration curve.